can start the presentation.
Ready?
Thank you.
Okay, can you see my screen?
Yes, we can see.
Perfect. Okay, thank you very much. I'm very excited to be part of this conference. So my name is Jessica Grove-Smith, and I work at the Passive House Institute. I'm part of the research team here, and one of my tasks is to provide climate data for the PHPP. So my presentation today is going to be about climate data, and more specifically about how do we account for the effect of urban heat islands, and how do we account for global warming and climate kind of generally becoming warmer. How do we take that into account in our Passive House modeling and in our PHPP? So as a starting point, the climate data is extremely important. When we design passive houses, it is all about designing buildings that have a high comfort level and a high level of efficiency for the specific location. So a passive house in a hot climate can look very different to a passive house in a cold climate. So the climate data really is a fundamental boundary condition for our energy calculation. Climate files that we currently have in our PHPP database. The colors indicate the different climate. Warm climate zone, some in the warm temperate climate zone. And we work the last couple of years closely with HomeGrid, with the partners, to make sure that we have a spread of climate data locations throughout Portugal. So this is where we are. People can send us an email and we assess whether a climate data in the region is already available or whether we have to create a new one. If there's a new one, we add it to the database so it becomes available to all PHPP users with the next update. The PHPP climate data generally is based on historical data, so on long-term data. A minimum of 10 years, 10 to 30 years is kind of the period that you need to describe a climate rather than just a year's weather. And we base the data, where possible, on measured data from actual weather stations or satellite data. So it's actual measured climate data that we use as boundary conditions. The question that I get a lot is kind of a question about the level of precision. Is it enough to work with reference locations, or do we have to work with highly localized climate files? It's very clear that the weather at an actual location will be different to the reference kind of climate data that we use in PHPP. Means that the energy demand that we calculate with our PHPP will be slightly different to the actual in-use energy consumption year by year. What's important to note that's okay, that's absolutely no problem, because this difference is small in comparison to kind of the overall savings of the user. So these two graphs that I show on this slide, on the left-hand, from the first passive house building here in Darmstadt in Germany over 25 years. And you can see there is a variation in the energy consumption for heating. It varies between monitors. It's not a problem. I mean, we still have a very high efficient building overall, and it's achieving what we want from the passive house standard. On the right-hand side, in comparison, you see kind of the savings between the low energy building on the left-hand side and between passive house on the right-hand side. So these small variations on an annual basis by weather really don't play a role at all. What we need to make sure is that we have typical climate conditions that are representative for that specific location. What's important to keep in mind, having said that, is that whatever climate data you choose as a reference location, is that you do not compromise in any way on the operation of the building and the comfort. So you have to make sure that you use a location that is representative in the climate conditions, that will allow you to optimize for the location. What I mean by this specifically is, in terms of not compromising on operation, is that you have to make sure your system is sized correctly. And what I want to focus on the topic of summer comfort. When we design a building, when we lay out the systems, we have to make a decision. Can we provide summer comfort alone with passive means, or do we have to provide active cooling in order to assure that we have high comfort also in summer? And this is a really important topic that that comes up a lot when we talk to clients, when we design buildings, when we get feedback for passive houses in use. Because we are dealing with global warming, the climate is getting warmer, and is predicted to be getting even warmer in future years when these buildings are going to be in use. And we also have severe urban heat island effects, where it's a lot hotter in cities than in the surroundings. So I want to focus on these two aspects a little bit and give you some ideas on how you can deal with this in your passive house design process. So first of all, a note on global warming. What you see here is an image of kind of the warming stripes, they are called, which is a very popular way of depicting kind of how the climate has been warming in the past. This is recorded data, so we know this is happening. We know that the climate generally is becoming warmer. And as I said previously, our climate data in PHPP is based on past data. So the question is, if we know warming, do we need to take that into account in our PHPP modeling? Should we be using climate data that it's already warmer than the past data shows? Graph is from the IPCC, the data that has been analyzed in terms of climate data projections. So on the top left graph is kind of the predicted temperature rise for different scenarios. So we don't know how the climate is going to warm. We can't predict the future, and it depends also on many different factors. It depends on how we implement our climate goals, whether the different countries actually act fast or not. So what you see here is kind of in red, the worst case scenario, whereas the blue line is the best case scenario. We don't know where we are going to be in reality in between. We also know that climate warming is very different depending on where you are in the world. So the warming is going to be more severe in some areas than in others. So there are various scenarios and calculation methods to predict the climate. Warming tends to take this into account in our energy modeling, but how do we deal with this? And I'll get to that a little bit later. The second situation that I want to reflect on is the urban heat island effect. Rome, Madrid, Paris, and Milan. And the red colors indicate higher temperatures. And it's very
Mais uma vez o pedido para desligarem o Wi-Fi, por favor, durante esta sessão, ok? Para tentarmos canalizar aqui a largura de banda suficiente. Ou então, podemos passar para...
on a local basis. So similar to kind of the climate warming, we say we know and we need to be aware of this and take it into account. But the question is, how do we do this in our modeling, in our design processes? So what to do? I don't want to just leave you with a question. I do want to kind of promote some ideas on this and encourage you to take this into account in your design decisions. The PHPP very much, I mean, it was made as a design tool, and the idea very much behind it is not to overcomplicate things, but to try to break things down to the essentials, to keep things as simple as possible, that you get robust and reliable kind of design guidance. And so we tried to do the same approach for this aspect of urban heat islands and global warming. How can we simplify this? How can we break it down and take this into account for the climate data boundary conditions we are using? So what we did is earlier this year, we released Excel file again which has the entire database of PHPP climate data integrated. You can select your climate file and you can say, I am assuming a summer temperature increase of a certain amount of degrees. It can be 1 degree, it can be 5 degrees, whatever you think is suitable. The tool will adapt your climate data accordingly so that you have higher temperatures during summer. And that adjusted climate data can then be reinserted into your PHPP and used as a boundary condition. So you're basically using the PHPP as normal, but with more pessimistic or with warmer temperatures during summer. And to show you an example, I'll show you an example in my next slide. Another comment here is that this tool is free. It's available on our website for download, and we do plan to integrate this methodology in kind of the next PHPP update so that people can automatically take this into account during the design process. So here is an example of the results that we kind of tested when using this approach. This is the example of the city of Munich in Germany. On the left-hand side, so what we see here is the overheating frequency, that's PHPP, for an example building. The first bar that you see here is for Munich, is on historical data from 61 to 90, which is actually the official reference period for climate in Germany at the moment. The building was modeled with a very low overheating frequency of only 1%, so absolutely fine, we can go ahead. If we actually use climate data of a more recent period, so 81 to 2010, which is the official climate data used by the World Meteorological Organization, you can see that the overheating frequency increases to around 4%. It's still fine, but there is an impact. The climate has warmed and the overheating frequency is likely to increase. And we can mimic this effect by using our climate data tool that I presented you on my previous slide, by using the old climate data and just adding 1.5 degrees as a summer correction factor. And we get very similar results, so in the range of 4% overheating frequency, the climate data set. Similarly, if we say, okay, we want to look at the impact within the urban context of Munich, what you see here is now on overheating frequency of 10%. So there's a significant difference between the overheating risk if you're building outside the city center of Munich or if you're building in the center. So you need to be aware of this. Again, using the simplified approach and saying we use the normal boundary condition in PHPP, but we add 3 degrees to account for the climate having warmed and to account for the fact that the actual project location is in the city center, we get that same, the same order of magnitude of a higher overheating frequency. So these are some examples of how you can use the tool to get an assessment of the impact of the hotter climates. The question, of course, is what kind of temperature increase do you use? Is it 1 degree, 2 degrees, or 3 degrees? There's a lot to say about that. It's a little bit difficult, and it's an individual case-by-case decision. The tool that we've released does include some guidelines in terms of what kind of temperature increases we recommend for urban heat island effect, and what kind of temperature increases we would recommend to model the climate projection. Before I close, I want to reflect a little bit generally on the comfort, because it is a very sensitive parameter and it is very difficult to predict in general, not only with PHPP, but generally energy modeling. How do we assess summer comfort? Partly because it's a very subjective thing, partly also because there's a strong influence of the user behavior. We don't know exactly how they're going to use the shading or the night ventilation or what the internal loads are going to be. So what I want you to take away from this also is to make sure that in your modeling you use realistic assumptions and you stress test the design. So see what happens if people maybe use less night ventilation. Is there a high risk of summer comfort, or can you be sure that a building will still perform well? The priority really needs to be that the buildings work and provide the high comfort and are healthy surroundings. So for you to take away, if you design your buildings and you do the stress test, you assess the impact of warmer summer temperatures, and you get to the point where you think, actually, maybe in 5-year time, this is going to be an uncomfortable building. I can't guarantee that we are going to have comfortable 25 degrees anymore. Then don't generally rule out active cooling. That might actually be the more sustainable and better way forward, and efficient active cooling systems are available, and it's better to plan them from the beginning. How we would approach stress testing. The PHPP includes the variant calculations. So in PHPP, you can assess or you can calculate variations of the night ventilation, for example, and see how that impacts and your design. That is something that I would recommend every. Stress testing for summer comfort. So that with PHPP very easily, you can kind of assess the overheating range of your building. So you can see the impact that a warming climate or the night vent expected to be, which will help to kind of risk-proof the designs and have more robust decisions in terms of providing summer comfort. I'm coming to a close. I want to kind of warming. We know that from historical data, and that's also what all the projections are telling us. So it's really important that you keep an eye out for summer comfort, especially in the urban settings. The reliability of your calculations is much more important than precision. It's very difficult to use a simple but robust stress test approach than to get it absolutely spot on right. So the simplified approach that we suggest by modifying the climate data is something that we recommend to use in your design processes. Conditions, but B, also to kind of assess the impact of user interaction in terms of night ventilation and shading. The second point I want to mention is if you model your building and you identify that there is a high risk of indoor temperatures during summer, don't tweak the numbers to make it work. It happens that people then kind of put unrealistic ask for different climate files that are maybe a bit easier to make the numbers work. It is our absolute priority to have buildings that provide high comfort and that work in terms of their energy performance. So tweaking the numbers is never a good idea. And keep in mind that active cooling with a passive house, we focus on high energy efficiency. So even if you do have active cooling, you have times perceived as a climate. We can implement very efficient solutions, especially in this whole context of global warming. Solution. Generally, make use of Design PH and PHPP as design tools. They are extremely valuable. And they will give you guidance in terms of where you stand and how you can improve your design to account for these. Things can be extremely harsh in terms of summer temperatures. Summer comfort is a design responsibility. So I hope I was able to give you some input on how we kind of recommend to deal with these aspects. To have conversations afterwards by email. My email is shown on the screen. Thank you very much for your attention, and I hope you enjoy the rest of the event. Thank you.